Let's go ahead and now take a look at division of fractions. This always seems to create a mystery for students that they don't know where the algorithm comes from. But let's first start looking at division of fractions, and the denominators are the same, right? So that there's some meaning to this. So 6 over 7 divided by 2/7. The answer is just 3 because we can look at it in the picture here. Here's 6/7 and 2/7. And if we think of this as what we call a measurement division, an extension of a measurement division problem, what we're asking is how many 2/7 fit inside of 6/7. So if you look carefully, there is 1, 2, 3, right? There's a 2/7, there's a 2/7, there's a 2/7. And so I see 3 groups of 2/7. And so there's my answer, 3. Where that leads us to when we think about from this approach when it has a common denominator is that we just divide the numerators. And so you can just go 12 divided by 4, 6 divided by 3, 16 divided by 2. But the key is to understand we're talking about the same relative pieces, right? The same 13ths, 17ths. And it goes back to understanding, right, that 6/7 is 6 groups of 2/7. And so you see the 6 groups of 1/7, and then you have 2 groups of 1/7. And so again, looking at those fractions in that way, knowing that they have the same denominator, right, we can then see how we just simplify this by how many 2 groups of 1/7 are in 6 groups of 1/7, and that answers 3. You can see it in the picture. That leads us to trying to solve problems that when they're not common denominators. But if you see, like in a problem like this, the old-fashioned way would be to invert and multiply. Would be invert to multiply, which is this rule here. We could just turn the second fraction into 35 over 40 because now it has the same common denominator. And now you could just divide. Once you have the same common denominator, 21 divided by 35. 21 over 35, or 3/5. When you get a chance to make up your own example to see what you got there so that you can see how that would work. But that leads us to the most common algorithm here, which is invert and multiply. You invert the second one, right? The reciprocal. When you invert, we're really saying is you're making a reciprocal for this here. And so looking at this here, you then have an algorithm to solve problems, right? And in order to do that, again, you will see, so for example, 4 divided by 2/3. The algorithm would be to do 4 over 1 times 3 over 2. So you get 12 over 6. And then the answer is 12 over 2, and your answer is 6. And again, I want to connect that back to your measurement, right, situation here. How many, so this question really is asking how many 2/3 are in 4. So here you see a picture of 4. And so what I end up having here is 2/3, that's 1. There's 2/3, that's 2. There's 2/3, that's 3. There's another 2/3, that's 4. Another 2/3 is 5. And then another 2/3. Here is 6. And so now that you have that, you can see why the answer is 6, right? It comes from this measurement model. You can read this here, little piece here to look at 3 divided by 1/2, why that equals 6. You can take a look at the visual there, right? And that's again viewing it as a measurement. How many groups of 1/2 go into 3? And so that's where you would have that. And so in summary, there are 3 equivalent ways for division of fraction. The common denominator approach, divide the numerators when it has a common denominator, right? And then invert the divisor and multiply approaches, which we have here. Looking at the shortcut here, you could also, again, on this problem, notice I turned this to 10 over 25 because it has a common denominator here, common denominator here, invert and multiply. So these are all different ways you would solve those problems here as you look through that, looking through my solutions there. And then lastly, there's kind of a unique way to solve these problems too, is through what's called the complex fraction approach. And so looking at this idea of complex fractions, 1/2 divided by 3/5. Take a look how this was written, 1/2 over 3/5. And what we do is we multiply the top and bottom by the reciprocal. And so notice the bottom then becomes 1 because these are reciprocals, and then the top just becomes 1/2 times 5/3. And you can see there's our motivation for the invert and multiply, why that works also. You're taking 1/2 times 5/3, which is 5/6 over 1, or 5/6. And again, that works is because we're multiplying the numerator and the denominator by the same value. And that's why that problem works there. So it's important to understand where that comes from more of what we call the complex fraction approach. It's also important to know before we move on to look at these problems here, division of fractions. Why is a division the same as a fraction? And so kind of walking through this allows us to do that. Any whole number can be written as a over 1 divided b over 1, and then we know the rule. So we can then see now division can be seen as a fraction also. So that's important to recognize that. That's just not it. It just that there's a reason why we can equate those two together. And then the last piece is to look at here is to just kind of how would we solve these mentally. You can see how I broke these up. 16 and 1/4 go together. So it's really 1/4 of 16 is 4, and then 25 times 4. Here I break the 24 and 4/7 up into two pieces here. And so then you end up with the 4 going into both. So that's your 6, and then 4/7 broken into 4 groups is 1/7. And then here I turn the 15 into 5 times 3. So if you look carefully, it becomes times 5 times 3 over 1. And then you can see those 5s become a 1. You just end up 4 times 3. Make sure you get a chance to read the book on how to write some, or look at some examples of word problems. Right, and what you want to do on these different problems here for each of these divisions is think about it from a measurements. How many halves go into 3? Here it's a whole number, so you want to break 1/3 into 4 groups of something. And here is, again, measurement. How many 1/4 go into 5/8?